welcome everyone. So this is the topic preview session for visible light communication. And my name is Zhou. I'm an associate professor from Dartmouth College. And today I'm happy to give you an overview on what is visible light communication, what has been done, and how is it different from the other modality of the communication that you have seen or we have been using today, and what are the new challenges remain. And in the end, we'll quickly go over some of the relevant papers in this year's MobiCom program. And hopefully that will be helpful for you to better understand and appreciate the papers in the program this year. So as the name suggests, visible light communication is all about using the visible light spectrum for data communication. So if you look at the whole spectrum of the radio spectrum, visible light communication, visible light spectrum sits between 430 to 770 terahertz, and that's the only band which is visible to our human eyes. And the wavelength is typically in between 400 to all the way to 700 nanometers. And depends on the wavelength, that will map to different colors that we perceive. And red color is typically having a larger wavelength. So if you see visible LED dials emitting lights around 600 all the way to 700, that's red light LED. And green is about 550. And then we have the blue light, which typically sits around 400 also nanometers. So based on the wavelength, you will roughly know the color. And the benefit of using visible light spectrum for communication is, there are a few. First of all, the whole bandwidth of the visible light spectrum is much, much wider than the total radio spectrum. Is actually 10,000 times wider than all the radio spectrum combined. And that gives you a lot of capacity to increase the data bandwidth that we are using today, and it's free of electromagnetic interference. So in scenarios like hospitals where you don't want to mess up with the medical devices, you probably, light communication is a viable option to support wireless communications in those scenarios. And it's everywhere because we have lights everywhere. So really give you the ubiquity of the connectivity. And most importantly, the energy for illumination can be reused for data communication, so it's more energy efficient as well. And lastly, because light is directional, so all the data are confined in a room, and it will be very hard to eavesdrop the traffic across rooms. So it's more secure than Wi-Fi or other radio communication technologies. So the idea is very simple, is that you can change the intensity of the light to encode the data. And depend on the luminaries, so you can change the light coming from the screen, your laptop screen, or other computer monitors, or it could be the luminaries that we're using for illumination, like fluorescent light, LED lights, or even visible laser dials. You can change the intensity to encode data. And the key thing here is that the change is happening at a very high frequency so that we cannot see, but the sensors can. So the sensors can decode the data while the light is providing illumination to the whole space. Yeah? So the sensors can range from the pin diodes all the way to image sensors or even cameras. And they have different trade-offs in the sensitivity and response speed. So, excuse me, yes. Can I ask questions in the video? Yeah, sure.
Okay, so one question I have is about the color. Can you actually change the color?
Change the color of
the light.
Right, so you will have to have multiple LED dials. Each has a different color. You cannot change the color of a single diode on the fly.
Right.
So you will have to have multiple diodes with different colors co-located, and then you can dynamically select the diode.
Okay, so my question is that if you are actually changing different colored diodes,
right,
each one of them is on-off, I understand, but the effective effective impact would be a particular color at the end, isn't it?
Right, yes.
So then in that case, the human can perceive the color, because you were saying that if we do it very fast, then we cannot perceive it. But how about the color?
Right, so there are multiple ways to go about it. One is the frequency of the changes. If it's happening at a very high frequency that exceeds our perception capability, you won't notice the differences. Another one is to utilize multiple color dials and try to complement the changes so that the changes are less noticeable. But as long as the changes at very high speed, typically you won't be able to notice anything.
All right, thank you.
Okay. And the slides are gone. Okay. Back again. Okay. So,
it would disturb it for others.
So there are a few factors affecting the date rate of light communication. So first of all, it really depends on how fast the transmitter or the luminary can be switched on and off. And so there are a few typical terms to describing the speed. One is called rise time, meaning how long does it take for the dial to increase the intensity from 10% all the way to 90%. And obviously, the shorter the rise time, the faster the luminary can react to changes in the current. And for the typical LEDs that we are having today, that's around microseconds, so not super fast. And you can estimate the modulation bandwidth based on the rise time by looking at 1 over the rise time. So for LEDs, off-the-shelf LED, the modulation bandwidth is typically in megahertz, tens of megahertz at most. If you're using the blue LED, they are the faster ones. And also another factor affecting the speed is how fast the receiver can react to the changes in the intensity. So that's called the response time, describing the speed of the photodiodes reacting to the changes in the light intensity. And that will depends on the type of the photodiodes that you are using. And typically they have an inherent conflict between the gain, how sensitive they can be to the incoming change of the light intensity, and another is the response time. So the smaller or the faster the photodiodes, typically the smaller the gain, and the slower photodiodes that typically have a higher gain, meaning they can sense lower light intensity. So that's typically a tricky trade-off depending on the application scenario. And lastly, the wavelengths really have a key impact on how fast the luminary can change. And blue light is the fastest one, and fastest one, and is often around 20 to 30 megahertz. And the yellow light is the slowest one, is only a few megahertz. So in some system setups, you will see people will have a blue filter in front of the photodiodes so that they're only looking at the changes in the blue light, because that gives you the fastest modulation bandwidth in general. Yeah. So in order to describe how the light signal is propagating over space, the typical model people use is called Lambertian propagation model. And that comes from a seminal paper published in 2004 by a research group in Japan. So it's essentially assuming the Lambertian radiation pattern at the source. So if you imagine that the LED is radiating all the photons in a sphere shape, and then depending on the irradiation angle, so you can estimate the amount of photons that emitted at a particular direction based on the irradiance angle, meaning the outcoming ray, the angle between the outcoming light ray and the surface norm of the luminary. So the M exponent here is called the Lambertian emission, and that depends on the beam angle. So if the luminary is emitting a 120 3 dB beam angle, then that M exponent will be equal to 1. So there are equations for you to calculate the exponent to get the equation right. And then you will see another term here That's the cosine theta. Theta is the incident angle relative to the surface norm at the photodiodes. And that cosine theta is to describe the angular response at the photodiode, meaning how sensitive the photodiode is for a given incident angle, for light coming at a given incident angle. So putting all things together, then you can calculate the received optical power using this formula. So we have a constant I0 here is representing the transmit power and the receiver gain, and then we have the Lambertian emission model describing how the irradiance angle affect the photons emitted at a particular angle, and another angular response at the photodiodes divided by the square of the distance. So that's the typical model people is using to describe the received power at a given location if you know the location of the luminary at another place. And there are a lot of emerging interest on using light for communication. So there is actually a IEEE standard defining the physical layer and MAC layer protocol, and they have considered up to tens of megabits per second data rate for visible light communication. And also, a group in UK has demonstrated 10 gigabits per second data rate is visible using micro LED. And they have 3 micro LED, each transmitting different data simultaneously. So each LED is about 3.3 gigabits per second. Together you get 10 gigabits per second in total. But keep in mind, this is based on micro LED, meaning they have very short distance, is around tens of centimeters at the most. So the distance is still a big challenge to support such a high rate light communication in practice. Yes?
So if you are transmitting with 3 LEDs,
yeah.
Do you need 3 photodiodes at the
Yes, you do, yes. So they have 3 color, blue, yellow, blue, green, and red. And then they have 3 photodiodes, co-located photodiodes, each with optical filter, so that each photodiode is only seeing the changes in one color, yes.
When you say co-located at the receiver, do they have to have separation, certain separation between them? Like in MIMO we have lambda over 3.
Right. It doesn't matter too much as long as they are inside the beam of the light. So as we will show later, there are fundamental differences between light propagation and RF propagation in general. Yeah. Okay, and there is even a startup in UK called Pure Li-Fi. You can actually buy a pair of Li-Fi access point and a dongle, USB dongle that can be plugged into your laptop, your tablet to establish a Li-Fi link. And this is integrating the modulation unit to a power line communication to connect the connectivity to the existing LEDs at homes or offices, and the data rate can go up to 40 or 46 megabits per second right now. And it's bi-directional, and they are using infrared for the uplink communication in the product. So if you're interested, you actually can buy a pair, and not super cheap, about a few thousand pounds, but it will be a nice starter kit to play with light communication and see the practical performance. Okay. So that's all the basics about what is visible light communication. And now I will briefly talk about how is it different from the conventional optical communication and how is it different from RF, including Wi-Fi, Bluetooth, and other radio technologies that we are using today. So if you really think about it, visual light communication is not new at all. And okay, the answer is here. I meant to have a quiz. What type of communication the first audio phone has used? It's actually visible light communication. Back to 1880 by Alexander Bell. So he invented a photophone, which actually translates the vibration of the sound to changes of the reflection of the sunlight. And then the sunlight will be reflected based on how the sound is vibrating in the air, and that the changes will be captured by a big mirror as a receiver, and they have a photodiode in the center to capture the changes in the light to recover the sound. And the whole setup can support up to 230 meters transmitter distance. So it's quite impressive that actually you already have visual light communication hundreds years ago. And then the technology evolves, and we have optical communication, which is using the waveguide to guide the light, propagate over the waveguide with near zero energy loss. And you typically have a cluster of the laser diodes, each transmitting different data simultaneously. So it can give you very, very high rate, tens of gigabits per second at least. And then not to mention have free space optical communication where you can remove the waveguide and have two high power, actually one high power laser emitting directional laser beam to the other receiver. And because of the characteristics of the laser light, it can support up to tens of even hundreds of kilometers transmission distance. So all these are essentially visual light communication, right? But so how is it different from the visual light communication that we are talking today? So to me, I think the key difference is really the technological evolution of LEDs, especially the blue LEDs. So that it's much easier to fabricate LED emitting white diffuse light. And it also significantly reduces the cost of LED. So it's now much cheaper to produce the same amount of lumens in comparison to other types of luminaries. And it also has a high efficiency of converting the electrical power to the optical power. And you see a wide adoption of LEDs today. So it made it possible to turn all the surrounding luminaries around us into wireless transmitters beaming data. So I think really the wide adoption of LEDs, which is also fast to switch on and off for transmitting data, made visual light communication different today, and also revive the concept of using visual light to provide ubiquitous connectivity to a wide range of mobile devices. So there are also a few differences from the conventional RF communication. So first of all the RF, the radio communication technologies, they can use modulation schemes that will modulate, that's capable of modulate the phase of the carrier. But that's not the case for the light communication. Why? Because first of all, there are no feasible technology today for you to manipulate the phase of the light. Maybe future nanotechnology will be able to do that, but not today. And even if you can manipulate the phase of the light, there are no devices capable of detecting the changes of the phase in the light as well. So as a result, all the light communication modulation schemes that you see today are purely based on intensity. So they are changing the intensity to encode the data. So it's called intensity modulation and direct demodulation, direct detection. And it ends up with a much simpler transceiver design in comparison to the RF counterparts. But it also means, although the visual light spectrum is 10,000 times wider than the radio spectrum in total, it doesn't mean you will have 10,000 times higher bit rate, because they are using completely different modulation schemes. Maybe with nanotechnology capable of modulating the phase of light in the future, we'll be able to better unleash the potential of the wide visual light spectrum. But today, we're limited by intensity-based modulation to encode data. So another difference in comparison to RF is, in RF communication, you typically need to worry about multipath propagation, right? How would that affect my reception reliability? But for light communication, it's actually much simpler, and it's mainly dominated by the line of sight communication. You might have multiple paths of reflection and scattering, but the energy from other paths are way weaker than the line of sight direct path. So as a result, you can focus the energy on the line of sight received optical power to estimate the performance of a single link. So it makes the modeling of the propagation much easier and actually more accurate than the RF communications that you see. And then lastly, I think that's the key difference between the light communication, the RF, which is the tight coupling with illumination. For RF, you don't need to, RF is imperceptible. You can modulate it however you want. But for light communication, you do need to be mindful about the speed of the changes of intensity because they are also, in the same time, providing the illumination to the space. So you do want to make sure that for the intensity-based modulation, the speed is high enough so that it won't cause any flickering effect to the user and cause any discomfort at the user as well. So oftentimes the threshold is 1 kilohertz, meaning any changes above 1,000 times a second will be safe for the user based on the literature. So that's a threshold to keep in mind if you are trying to modulate the changes of the light. Yeah. Any other questions in the meantime? No? Yes?
Very quick question. What's the range?
For the range for
visible light communication?
Right.
What's the distance you can achieve?
Right. For now, it's about a few meters. I think a few meters. So if you look at the product from Pure Li-Fi, it provides up to 5 meters, I think. So it's sufficient for room level network. But if you want to get longer distance, you can increase the power at the luminary to get a longer distance. Or more sensitive photodiode as a receiver can do as well. Yeah. Yeah.
Does the ambient light affect the receiving capability?
Yes, so that will depend on the type of modulation scheme that we're using. So as I will show later, if you're using frequency to encode data, so it will be more robust to ambient light changes because ambient light changes almost randomly. So it's close to the DC current, DC component. You can use FFT to project the changes to a frequency domain and filter out the ambient light interference. But if it's based on purely intensity, it will be more vulnerable to ambient light changes, and we probably need per symbol training before transmitting each symbol to get a sense of the current ambient light so that we can cancel out the current ambient light interference as well. But it's more overhead, yes.
One of the experiments you showed that you have demonstrated 10 gigabits
Yeah.
to use the light communication.
Right.
Now you said LED there were limited bandwidth, 30 megahertz.
Right. Yes. Yes.
So how are you using IMDD? They were able to get this 10 gigabit or 3.3 further.
Right. So if you think about the physics, the switching speed of the LED is determined by the carrier's lifetime, which is around a nanosecond. So meaning if you have an ideal LED diode, you technically should be able to approach 1 gigahertz modulation bandwidth. But in reality, because of the junction capacitance in the LED chipset, you will have much lower bandwidth than that. So really because of the junction capacitance of the LED chipset. And the larger the LED chip, the higher the junction capacitance, meaning the lower the bandwidth. So that's why they demonstrated the gigabits per second data rate using micro LED, which has a smaller size, meaning smaller junction capacitance. But with a larger LED, which we typically use for illumination, we won't be able to get.
So those are the specific LEDs which are
Yes, micro LEDs.
LEDs which are used for illumination.
Right, because these need to be high power. If they are high power, then the size won't be small, and then you have high junction capacitance. Yeah. Okay. So what has been done? So actually, in our community, we have 2 directions related to light communication. One is to look at the communication itself, to see how to advance the speed and how to increase the reliability of the communication. And another is to use it, in the meantime, also reuse it for sensing, to sense user behaviors from whole body gestures all the way to even the substances in the blood. So I will give you an overview on what has been done in each category. For the communication, there are a lot of modulation schemes proposed in the literature, all from the simplest one of key, meaning if the light is on, that's speed 1, if it's off, that's 0, to frequency shift key, meaning you can encode the bits into the frequency of the switch of the light changes. Like if you change the light 1,000 times a second, that's 1, 2,000 times a second, that's 0, for instance. So that's frequency shift keying, and then you have the amplitude-based modulation, the width-based modulation, the position-based, the color shift keying using the color to encode data, or spatial keying, meaning the position of the light can encode the bits as well. And you have polarization-based modulation scheme and OFDM, and maybe your design in the future as well. So these are actively studied, in particularly in the electrical engineering domain. So you will see a lot of papers published in EE proposing improved designs in the modulation to increase the bit rate. But most of the works you see are looking at a single link and oftentimes with simulations. So I think that definitely there are more opportunities for our community to look into the practical system performance of these schemes. Yeah. So in particular in our community, we have looked into how to make it more robust by tackling the inherent challenges of light communication. There are a few. First of all, it's very easy to block it, right? Because of the wavelength is in nanometers, so any macroscopic objects can completely block the light. So how can you maintain a reliable transmission with occasional blockage of the light signals? And another is the distance, and also related to the wavelength. So the degradation of the signal is much bigger than the other communication modalities. So it also means the distance is also limited. For Wi-Fi, you can get up to 100 meters transmission distance, but for light, like for the typical intensity that we're using for illumination, is only for a few meters at most to transmit data. And also you have the uplink issue, right? Even though the product is using near infrared, but how can you, is there any options for you to still use visible light for realize a reliable uplink communication so that it's fully bidirectional? That's another open challenge. And then lastly, light is not always on, so, but you do need connectivity all the time. So how can you balance these two cases as well? So I will give you some examples on each.
For the uplink,
right.
Do you need a receiver in the light?
Yes, you do.
So these are not the conventional lights. I have to buy new lights.
So you will have to modify the existing lights. So first of all, you will be connecting a modulation unit to the existing light anyway. Okay. And then you need to physically co-locate photodiodes with the LED diode so that the light can receive data in the same time. Yes. Yes.
Question about the distance that you mentioned, that you can't get similar distances with light.
Yeah.
Is that because of scattering?
It's mainly because of the amount of degradation happening over distance. So typically the higher the frequency, the larger the degradation even for the same distance. So that's why the degradation of the light energy is much higher than, say, Wi-Fi, Bluetooth, or the RF.
If you think of it as electromagnetic radiation,
right.
And if the channel is free space,
yes,
then there should not be any difference.
If you look at the free space formula, lambda is at the, you will see the relationship between the wavelength and the free space loss. So the larger the wavelength, the smaller the loss. So meaning for light with nanometer wavelength, the higher the energy loss.
So then you're assuming that the photodiode scales with with light.
Yeah, so you will have to either increase the directionality to increase the distance, or increase the power, or increase the gain at the receiver to maintain the same distance. Yes.
Or maybe I'm going to talk about it further, but how severe is the blockage of that process? Like, for instance, if I put it on a smartphone and cover it with a pen, are there any chances I could transmit anything, or can it penetrate the pocket?
Right. So the material plays an important role. I think for a thin cloth, probably won't be able to, especially translucent cloth, you won't be able to completely block the light. And also depends on the sensitivity of the receiver. So if you have a super sensitive photodiode, which is able to count the photons, for instance, there are photon counting devices. So if you have devices with that high sensitivity, then it will be more likely that you can still decode some data, even if there are partial blockage between the transmitter and receiver. Yeah.
And also, when you block it, the line of sight is blocked.
Yeah.
But you always get something from
non-line
of sight.
Yes.
From the wall, something is getting reflected into your device.
Right. So yes, if you have a sensitive photodiode, you might still be able to see a few photons coming from other paths, but all depends on the sensitivity of the receiver. Also, if you have a good reflection surface, even if the line of sight is blocked, you can turn to other directions to get the reflected signal go through and arriving at the receiver as well. So there are potential options to deal with the blockage issue. So for the uplink, I want to highlight a few works in our community, which is essentially backscatter the existing light signals. So the idea is, at the receiver, you can have a LCD shutter covering a retroreflector. So the retroreflector is the material capable of reflecting the light along, bounce back along the same direction as the incident angle. So by modulating the LCD shutter will determine whether the light will be reflected or not reflected. So you are essentially modulating the reflection property of the LCD shutter to encode data. So the benefit is you don't need to actively generate light signals. You can reflect existing light signals from the luminaries, so it's entailing lower power consumption for the receiver to transmit data back to the infrastructure. And so it's a very good option for building a VLC uplink, right? Because the uplink, the key issue is the power consumption. If you have a LED always on the phone, the battery probably is draining pretty quickly. So this is a nice way to allow you to still encode data by using light, but with a very low power. So the downside is the speed. So it's all limited by the LCD shutter, and that gives you only hundreds of, up to 100 bits per second data rate. Probably the recent development achieves up to 1 kilobits per second data rate, but still very limited. That's a key concern, but it's a very interesting idea to reflect existing signals for transmission. And for
in the previous slide, what's that solar panel doing?
So this is harvesting energy in the same time, so that I can power the other components. And the goal is to see if can mitigate the energy overhead of the whole transceiver.
And is harvesting from the same VLC source?
Yes, it's harvesting from the same source. Yes.
So what sort of form factor do you need for that?
So the solar panel is around a credit card sized, but it can be made larger, depends on the device, right? And the LCD shutter and retroreflector is probably half the size. So
this is if this is my smartphone, then I need a solar panel in my smartphone?
So there are actually translucent solar cells available right now. So you can imagine in the future, the screen of your phone can be a solar cell harvesting energy from the light. And then in the meantime, you can have the LCD shutter to modulate the reflection, non-reflection to encode data. So, and you can also surround your phone surface with solar cell films, which are very thin and flexible to increase the sensitive area and also the harvested energy as well. Yeah. So for the light not always on, there are cases where you don't want to have the lights on, like during the night when you're going to sleep, or in a sunny day, you really don't need any indoor illumination, or for the phone to talk to the infrastructure, you also don't want to shine a light, which consumes energy and also visually unpleasant. So there's a work, another option which is to consider infrared, right? So infrared, you do need additional emitters for that to happen, and also it will have eye safety issues, especially if you want to support too early. If you want to support a long distance communication, and infrared is imperceptible, so it's really hard for the user to avoid the light beam for eye safety. So what are there other options to still realize communication, even if the light is appearing off? So there is work called dark light, which is using very short light pulses to transmit data, because the pulse is so short and also is happening at a very high frequency, so you won't be able to notice anything, but the sensors can, so the communication can be maintained when you don't want any indoor illumination. So this could be a potential solution for the uplink as well, given the low power consumption of this approach. I think the date rate, again, is the key challenge, and the current prototype can support up to 1.6 kilobits per second. Might be okay for some applications, but we do need better solutions to increase the date rate for VLC uplink. Yes?
Does the fact that I cannot visually see the pulse mean that the pulse is not anyhow badly affecting my eye, or somehow, bringing some pulse issues? So does the fact that I cannot recognize that there is something happening there, meaning that there is actually nothing harmful happening?
Yeah, that's a good question. There haven't been any long-term user study to see if there are any long-term health issues. So I cannot answer that with a definite answer, but based on the experiments shown in the paper, so it is fine for users in a diverse age range.
Everybody who participated, they survived, right?
True. Yes, and the experiment lasts long. Yeah. Okay, I'll skip that. This is not working very well. Okay. And the distance, I want to mention this particular work is a paper published in MobiCom last year. So this is trying to see how to increase the distance of light communication by using the polarization as a way to encode data. So essentially, light communication, the distance is small is because if you think about each pixel or each photodiode, right? The photodiode essentially is integrating all the photons arriving in a particular interval and report an intensity reading. So that means that the faster the light change, the shorter the interval the photodiode has to accumulate all the photons arriving in that interval. So that means if you are changing the light at a very fast speed, the distance will be small. So this paper is trying to achieve a better balance by modulating not directly the intensity, but the polarization of the light, which is imperceptible to our eye. So as a result, you don't have to modulate the light intensity at a very fast speed. You can change it at a slower speed, which is really beneficial for supporting long distance. But in the meantime, it won't cause any imperceptible light changes. So it's still okay for illumination. So this is a very interesting idea published in MobiCom.
Sorry for the ignorance. What is polarization?
So the light wave, when the light waves propagate in the air, is essentially a combination of the magnetic field and electrical field oscillating in orthogonal directions. So the oscillating direction of the electrical field is the polarization of the light. So that's imperceptible to our eye. And the typical light that we see, the sunlight or the light from the LEDs or fluorescent light, they are unpolarized, meaning they're containing oscillating directions in all directions. so meaning they are unpolarized. And what this paper is trying to do is to add a polarizer in front of the LED to allow only the light waves of a given polarization direction to pass through, so that you get polarized light. And then they have a disperser to disperse the polarization direction by a certain amount to modulate the bits. And because the change is imperceptible, so you can modulate at a lower speed to increase the distance.
So just quickly, 2 questions.
Yes.
So can a photodiode detect the polarization, or you need a camera?
You need a camera in this case.
Okay.
So because they are essentially translating the changes to polarization to the color change.
Right.
So because they are disperse the polarization in the wavelength domain, meaning depending on your wavelength, the amount of polarization change will be different. So maybe the red light now is having a 10-degree polarization direction, the green light is having 30-degree polarization direction. Then if you add a polarizer in front of the camera, then you will see a particular color based on how much the polarization has been changed.
So if I'm using my smartphone for communication, I have to turn on my camera?
True, yeah, for this work.
For this work, polarization?
Yes.
And how many different polarizations you can have? I can switch between how many? It's just two different directions?
It's continuous, because it will be translated to a different RGB pixel values at the camera. Because depending on how much you are dispersing the polarization of a given wavelength, you will map to a different color seen by the camera. So then you can use the RGB values at the camera.
So I can have many different levels of polarization?
Yes, so you can modulate.
Yeah, so is it effectively similar to having phase detector? So I can have many different phases. This is for phase, I understand, but in effect, for modulation point of view?
Yes, I think so, yes. But at a very low speed. And then there are a subclass of light communication which considers the screen as the transmitter and the cameras at the receiver, and that's a screen camera communication. Yes.
I have one more question regarding polarization. So you keep mentioning that the speed is much lower.
Yeah.
But you get the same data rate, or?
Yeah, the data rate is lower as well. So the goal for the previous paper is to increase the distance. They are able to get 40 meters transmission
so the fact
distance.
That they have the signal always on allows them to have a longer distance.
The fact that they are modulating the changes at a lower speed increases the distance, because the lower the speed, the longer the integration window for the photodiode. Yes. So
the camera has more time.
Yes. Okay. So that's a subclass of light communication which have the screen and the camera. So you can divide it to 2 categories. If you look at all the papers published in MobiCom, MobiCs, so one category is to use the visible code displayed on the screen to encode data, and then the camera can detect the code, and then depending on the encoding scheme, you can recover the bits encoded in the code on the screen. So all the papers that you see in this category is trying to improve the code design so that you can pack more bits into a given code, and also to allow the detection at the longer distances as well. And another category is more recent, is to see how you can hide the code into the existing screen content so that the camera can still detect the changes of the pixels and decode data, but we won't be able to see that, and so you can still use the screen as you would like to. You can use it to see videos, play games, but in the meantime, the screen is transmitting data simultaneously to the camera. So it's providing a secondary channel, communication channel to the camera. So I think the benefit is really the physical association of the communication and the screen. So it will be useful for, say, augmented reality or other applications where you do want the physical association of the screen and the data. The downside is the speed. The data is often a few kilobits or hundreds of kilobits per second, so not super high. And actually, there will be a paper in this year's MobiCom proposing a new imperceptible screen camera communication. So I will briefly talk about that later. So that's all about the communication side. And then there are another categories of works that you see published in this community focusing on the sensing aspect, how to reuse the same medium, not just for data communication, but also for behavior sensing. So the sensing capabilities range from the occupancy detection. This one is not occupancy detection to activity estimation, to recognizing gestures, to do indoor localization, to recover a skeleton pose, or even to infer finer-grained biometrics. So I will focus on the last three because these are harder than the first three. The first three is mainly classification. You are trying to differentiate a few poses or activities, but the last three are harder. Yeah. So there are many papers published on using light for localization. We can divide them based on the methodology. So the first category of the works is based on the received signal strengths. So the idea is if you can separate the light signals from different luminaries, you can estimate, based on the intensity you received from each light, you can estimate the distance to each luminary, and then you can use triangulation to determine your location. Yeah, so this was a paper published in NSDI 2014, and they implemented a light beacon at the luminary side to allow the receiver to separate the signals from different light sources. And another category is based on, it's similar, it's also trying to identify or differentiate different light sources, but this is leveraging the rolling shutter effect of the camera, meaning if the light is flashing at a different frequency, depending on the frequency, then you will see a different pattern at the camera. And then you can use this pattern to separate different light sources. Again, if you know the locations of the light sources, you can do triangulation and determine where you are. So these two are very similar, but they differ in how you encode patterns into each light source so that the receiver can differentiate different light sources and then later do triangulation. And then there's a few papers that you see published in recent years which utilizes polarization for localization. And the first paper published in MobiCom 2015, they are using the polarization to encode or to transmit the light ID from each light source, so that again, if you know, you can separate the light from different sources, triangulation, blah, blah, blah. You can do the same. Yeah, but this is based on polarization to encode the light ID. Yes?
So in the literature, do you know how many different levels of polarization people have used so far?
Different levels of polarization people have used. I don't recall right now, but
right. So in that example where you were using light polarization to separate different lights, so if I have 100 different lights, then I need 100 different polarization levels, right?
So the dispersion of the polarization is continuous, so that should be fine.
Yeah,
and also they are literally transmitting data using the polarization-based modulation. So I don't recall the detail, frankly, but I think they consider the collision of multiple lights, yes.
So all of these three methods, the receiver is a camera, not a photodiode.
For the first one, the ISS-based, the receiver is a photodiode. And then for the light polarization, I believe a few are using photodiodes as well. Not all of them are using cameras, yeah. And then there are two more recent MobiCom papers looking at how you can project a pattern of the light polarization into the space so that the devices can detect the pattern at a given location and identify the device location. And the MobiCom 2017 paper is using active unit to change the polarization dynamically so that the device can detect the changes in the polarization and determine the location. And then the paper in this year's MobiCom is more passive. So they are adding a transparent tape in front of the light cover to project a static pattern of light polarization and consider a combination of light and inertia sensors to determine the location of a device. So they are all different methods. But they all require modifications to the existing lighting infrastructure, right? They either modulate the current of the light or adding a LCD, adding a modulation unit to change the polarization or transparent tape. So there are a few papers looking at how you can leverage the inherent physical features of the light to separate different sources and then do triangulation and so forth. So what they observe is that off-the-shelf LED is often, including fluorescent light, the inherent flashing frequency is actually different from one another. So you can use the differences in the inherent flashing frequencies to differentiate different light sources. But again, this is really a hardware artifact. So it's an artifact of the LED driver. So maybe as the LED technology advances in the future, you will see fewer differences in the flashing frequencies across different lights. But so far, they have demonstrated that by using these small differences across different lights, they are able to differentiate them and do triangulation and so forth, localization. So there are 3 papers published along these lines. So starting from using cameras as a receiver and all the way to using photodiodes as a receiver to do localization. So this is localization. And there are papers, and also, yes?
How difficult or how easy to make the LED detachable from the system so that once its lifetime is over, you can replace it with another LED?
You mean how can we detect the aging of the LED? You will notice the aging of the luminary by seeing the gradual dimming of the light, I assume, right? And also LED is actually much more durable than other types of lights.
Even after 2 years, 3 years, you may need to replace the LED with a newer.
So if you look at the Li-Fi product that I showed earlier, they have a separate modulation unit. You can connect to your existing LED. So it doesn't affect the connection of the LED that much. You can easily replace the LED if they are aging over time. So it should be easy to replace based on the videos that I see on the website. Yeah. And there are works that are trying to recover finer-grained user behavior, not just the location, but also the skeleton pose of the user by just observing how the body is blocking the light. And typically they rely on deploying sensors in the environment to aggregate observation at different locations to recover either whole body poses or hand poses as well. And even your gaze. So this is a work published in Census 2017. So it reuses the light from the VR screen and then see how your eye is reflecting the screen light to recover the pupil position. So that's another use of the light sensing. Has nothing to do with communication, by the way, but it's a way of using the light as a medium for sensing the user behavior. And another paper also published in Census 2017 reuses the flashlight of the phone to sense the oxygen level at the blood. It's a non-invasive method, so you don't need to draw the blood out of the finger frequently for the monitoring of the blood oxygen level. So it's all based on how light of different wavelengths is interacting with oxygen in the blood. So that's another example of using light for sensing finer-grained biometrics of the user. So lastly, what are the remaining challenges? We have looked at what has been done in this area. So here are my 2 cents on what are the remaining challenges. First of all, as you can see, all the works have been focusing on using existing LED luminaries, but existing LEDs are limited in the modulation bandwidth. So regardless of the type of the LED, you can either have the blue LED with the yellow phosphor to generate the white light, or have RGB co-located LED diodes to generate the white light. For both types, the modulation bandwidth is relatively low. It's only around tens of megahertz at most. And micro LEDs can go faster, but they are limited in the distance, as we mentioned before. So all the works you have seen, all the system prototypes you have seen, the date rate are limited to tens of or hundreds of megabits per second at most. So it's really far behind the actual potential of light. So I think down the future it will be interesting to see how can we go beyond existing off-the-shelf LEDs and use some of the newer lighting luminaries for communication. Example includes superluminescent diode or SLEDs, or even laser diodes. You can have it diffused to generate white light, but they will give you much, much higher modulation bandwidth. And in the meantime, you can reuse it for illumination. So I think as a community, we should be not constrained by what's already on the market, but also be open to try some of the newer luminaries and see how we can further unleash the potential of the light communication. So this is just a comparison of the emission profile of different luminaries from the laser to SLED to the LEDs. And they have very different emission spectrum profiles as well as the beam angle. But in the interest of time, I won't go into the detail. I'm happy to talk to you afterwards if you want to hear more on that. And another challenge is on the receiver design. We have a receiver problem. If you want to achieve gigabits per second date rate reliably, you do want something that will be able to react fast and also maintain a low power consumption in order to use it across a range of mobile devices. And so that's an open challenge to solve as well. A high-speed, reliable uplink is yet to come. We do see the use of near-infrared as an alternative for uplink communication, but whether there are better approach that's another open challenge that we can think about. And as I mentioned earlier, a lot of the works are looking at a single link. So it will be interesting to go beyond a single link and really have a testbed of VLC links in the network and to look at some of the practical challenges when we have a network of the light link to provide reliable communication, even with the user mobility. How do you handle the handoff as a user is moving from one light to another? As you can see, the coverage of the light is very small, so you will have frequent switch across different luminaries. So how to handle that? That's a system challenge down the road. And also with real more deployment and testbed building, we'll potentially have more demonstrations of the killer applications of light communication as well. Okay, I think personally, this is a very fun topic to study. And because it's so interdisciplinary, and even inside computer science, graphics and vision has very well understanding of how the light is propagating in the air. So there are a lot we can learn from graphics and vision and see how we can follow the propagation modeling to optimize the networking and communication performance. And because light is visible, you can use it as a display. So there are a lot of interesting, innovative human-computer interaction systems that you can envision by using light. And also using light sensing to facilitate robotics applications. And light is directional, so you have more secure than other wireless communication. So the security and privacy aspect is also interesting to investigate. And outside CES, we should be aware of the advancement in optics, photonics, material science, bioengineering. I think all the advances happening in those fields will also be relevant to the light communication. For instance, if there are better LED luminary design capable of having higher bandwidth, modulation bandwidth. That would be interesting to investigate. And also there are current nanotechnology investigating how you can modulate the phase of the light. So if you can modulate the phase, then you can even realize higher rate by utilizing the wide bandwidth of the visible light spectrum. So I think overall it's an interesting interdisciplinary topic to study, and we shouldn't be constrained just by what's happening in our community, but also be open and mindful of what's happening in other fields as well. Yeah. So lastly, I will quickly go over a few relevant papers in this year's program, relevant to light communication and sensing. There are 4 papers in total, and 3 of them are about sensing. Only 1 is about communication. So the first one is actually happening probably a moment later. So this is about how you will be able to use light to sense the pupil size and movement, all without a battery, because you can harvest the energy from indoor lighting to power the whole eye tracking system. So that's happening very soon. And another sensing paper is called Light Steer. So it will be presented tomorrow morning. So it's a very interesting idea of combining light sensing with millimeter wave, because these two have very similar propagation characteristics. So you can use one as a medium for sensing to sense the direction of the transmitter, and then you can really help to speed up the alignment issue, the beam alignment of the millimeter wave communication link. So this is a very interesting paper. Highly encourage you to attend the talk. And then we have another one. This is about localization using light, and it's also leveraging the polarization change of the light, and they have attached the transparent tapes in different patterns to each luminary so that you get a different color pattern for different light. And again, once you can differentiate the lights, you can triangulation and so forth to the localization. Yeah, so this is a light localization paper happening tomorrow afternoon, probably the last paper. And then lastly, you have the communication paper, which is on the screen camera communication. So the paper is trying to improve the modulation design of the communication so that you can reach a higher throughput and with better reliability. And this is their comparison of the proposed system in comparison to all the prior unobtrusive screen-to-camera communication. So you see they have higher throughput while maintaining imperceptible to the eye. So this will be happening in the last day of the main conference, I assume. So that's all. That's the 4 papers related to light communication and sensing. And I hope what we have discussed here will be helpful for you to better appreciate the papers to be presented in the conference. Yeah, I hope it's helpful. Okay, thank you everyone.